Today we will understand the topic of magnetic field due to an electric current. We have seen that magnetic field and electricity are closely related. Let's find out some properties of magnetic field produced due to a current carrying conductor. Now let's see an activity on it. A thick copper wire is placed vertically on the cardboard. Magnetic compass is kept near the wire. When current flows through the thick copper wire, magnetic field is generated. If we position the compass at different locations near the wire, needle points in different directions. Same activity can also be performed with the help of iron filing. Iron filings are spread in a circular fashion around the wire. Concentric circles formed around the wire represent magnetic lines of force. Direction of magnetic field also depends on the direction of current flowing through the wire. Reversing the direction of current also reverses the direction of magnetic field. This can be easily explained with the help of right thumb rule given by Maxwell. Imagine you're holding a current-carrying wire in your right hand so that the thumb points in the direction of current. The direction in which fingers wrap the wire will be the direction of magnetic lines of force. Just like the right hand rule, we can find out the direction of magnetic field if screw is assumed to be held along the conductor and the screw is rotated such that it moves in the direction of the current. Direction of magnetic field is same as that of the rotation of the screw. This activity helped us to understand nature of magnetic field around straight current carrying conductor. Strength of magnetic field reduces as the distance from the wire increases. Therefore, the concentric circles representing the magnetic lines of force are shown bigger and less in numbers as the distance from the wire increases. We just saw properties of magnetic field produced due to a current carrying conductor which was a straight wire. What will be the nature of magnetic field when the current carrying conductor is a loop? Let's perform this activity. Cardboard is used to make a large loop of coated copper wire with 200 turns. More turns ensure that we get measurable magnetic field. This loop is placed in the cardboard slot as shown. Both ends are filled to remove coating and are connected to the power source, made up of 4 AA batteries. Placing magnetic needle compass at the center of the loop indicates the direction of magnetic field. Reversing polarity changes the direction of needle. Same exercise can be repeated with more number of needles placed at different locations around the loop. Can you try this activity by increasing the number of loops, by increasing the size of the coil, or by increasing the current through the loop? When a copper wire with a resistive coating is wound in a chain of loops, like a spring, it is called a solenoid. One of the open ends of a solenoid acts as a magnetic north pole and the other end acts as a magnetic south pole. This is very similar to bar magnet, which has north pole at one end and south pole at the other end. Intensity of the field inside the solenoid is uniform. Let's measure it with the help of this simulation. You are aware of the magnetic lines of force of a bar magnet. The properties of the magnetic field of a solenoid are very similar to the magnetic field produced by a bar magnet. When a current-carrying conductor is placed in a magnetic field, it experiences a magnetic force. Let's find out the direction of the magnetic force by doing this simple activity. North and south pole of ring magnet unit is defined. North pole marked as white. Freely suspended rectangle-like copper wire piece can move freely in horizontal direction and can be still form part of the circuit. When current is passed through the wire, force acts on the field and it moves towards the battery. Reversing polarity changes direction of the copper wire. This behavior can be explained by Fleming's left-hand rule. The thumb represents the direction of the thrust on the conductor or the motion of the conductor. The forefinger represents the direction of the magnetic field, North Pole to South Pole. The center finger represents the direction of the current, conventional current from positive to negative terminal. Factors affecting magnetic force on a current-carrying conductor in a magnetic field: the strength of the magnetic field, current flowing through the wire, and the length of the wire. Try variations of these factors and do the activity. Force is 0 when the wire is parallel to the magnetic field. Can you verify this as well?